Resistor transistor logic, RTL, also referred to as transistor-resistor logic, TRL, is a type of digital circuit that utilizes resistors in the input network and bipolar junction transistors, BJTs, as the switching components. It stands as the earliest form of transistorized digital logic circuitry, paving the way for subsequent technologies like diode transistor logic, DTL, and transistor-transistor logic, TTL. Originally assembled using discrete elements, RTL marked a significant milestone in 1961 by becoming the first digital logic family to be manufactured as a monolithic integrated circuit, a breakthrough that found practical application in the Apollo guidance computer developed from 1961 and launched in 1966. In the implementation of an RTL inverter, the fundamental RTL gate known as an inverter, or NOT gate, responsible for logical negation, is crafted using a common emitter stage with a base resistor linked between the base and the input voltage source. The base resistor's purpose is to amplify the minuscule transistor input voltage range to the logical 1 level by transforming the input voltage into current, striking a balance between being low enough to saturate the transistor and high enough to yield a high input resistance. Conversely, the collector resistor's role is to translate the collector current into voltage. Its resistance is carefully selected to saturate the transistor adequately while providing low output resistance for high fan-out. A more complex iteration of the RTL gate is the one-transistor RTL NOR gate, where multiple base resistors transform the inverter into a two-input RTL NOR gate by simulating logical operations akin to addition and comparison. This configuration involves a network of resistors acting as a parallel voltage summer with equally weighted inputs to drive a transistor acting as a voltage comparator. Moving beyond the constraints of single-transistor gates, the multi-transistor RTL NOR gate addresses limitations through a series of parallel connected transistor switches, enabling an unrestricted number of inputs by isolating them from each other and mitigating issues related to the leakage current of cutoff transistors at logical 1 output. This innovative approach was later adopted in the development of various gate technologies like DCTL, ECL, TTL, 7450, 7460, NMOS, and CMOS. The stable and predictable performance of bipolar transistors in RTL circuits hinges on the appropriate biasing of their base inputs, ensuring operational reliability. RTL technology gained prominence for utilizing a minimal number of transistors, particularly advantageous during the era of discrete component circuits when transistors were costly to manufacture. While early integrated circuits initially followed this approach for logic production, they swiftly adopted more high-performance circuits like diode transistor logic and transistor-transistor logic. One drawback of RTL is its significant power dissipation when the transistor switches on due to current passing through the collector and base resistors. Consequently, RTL circuits necessitate a higher current supply and enhanced heat dissipation. In comparison, TTL circuits with a totem pole output stage reduce these power and heat demands efficiently. Another limitation of RTL is its restricted fan-in, typically capped at 3 inputs for many circuit designs, affecting noise immunity. Integrated circuit RTL NOR gates, however, offer flexibility with multiple logic inputs, even accommodating examples like an 8-input NOR gate. In terms of speed enhancement, various methods have been applied to discrete RTL over time. Companies have sought to boost the transistor switching speed by using higher frequency transistors, capacitors, or employing diodes for negative feedback to prevent saturation. Additionally, techniques like using capacitors in parallel with input resistors, high collector supply voltage with diode clamping, and incorporating diode networks known as Baker clamps for reduced transistor saturation have been explored. These methods have not only increased speed but also optimized performance in both discrete RTL and integrated logic families, such as Schottky TTL, by integrating Schottky diodes to prevent transistor saturation effectively.